I was sitting there this morning typing a prompt into ChatGPT. I think I was asking it to debug some code.
Mhm.
And I had this moment where I just stopped and thought, this is it.
This is it, meaning what? The peak.
Exactly. The interface is clean. The answers are pretty much instant. It feels like the Transformer, this engine running everything from Claude to Gemini, is the end of history for AI architecture.
Right.
Like we finally built the combustion engine, and from here on out, we're just, making the car slightly faster or adding nicer leather seats.
It definitely feels that way to the user.
Yeah.
I mean, it's become our digital oxygen. But if you look at the stack of papers landing on my desk this week, we are not looking at the combustion engine.
What are we looking at then?
We're looking at the steam engine. And there are people, I mean, heavy hitters from Stanford, Google DeepMind, OpenAI, even one of the original creators of the Transformer itself,
Mm-hmm.
who are basically saying the steam engine is about to be scrapped.
Scrap. That sounds aggressive. I mean, these companies are pouring billions into these models right now.
It is aggressive.
But the premise of the research we're diving into today is that the large language models we're all obsessed with are technically on their way out. The claim is that in the next 18 months, the AI stack is going to look radically different.
Okay, that is a massive claim. So that's our mission for this deep dive. We are going to look at why current AI has supposedly hit a wall, even if I can't quite feel it yet as a user, and we are going to break down the 5 specific technologies that are poised to replace it.
Yeah, and we're talking about everything from diffusion applied to text all the way to machines that think in these continuous time spirals.
Let's start with the problem, though, because to me, the current text seems to work just fine. Why are these researchers saying it's broken?
It comes down to a fundamental flaw in how they write. See, current models are autoregressive.
Which means,
It means they are strictly linear, they write left to right, one word at a time. Imagine a typist who is incredibly fast, but their keyboard has absolutely no backspace key.
no backspace. So if they mess up the first word of a sentence, they're committed. They have to twist the rest of the sentence to try and make sense of that first mistake. They can't just stop, look at the whole paragraph and say, actually, that intro was weak, let me rewrite it.
They're just predicting the next token over and over and over.
Right. And think about the computational waste there. For a standard response, the model is running its entire neural network loop.
Billions of parameters.
Billions of parameters, just to produce the word the.
Mhm.
Then it takes the, feeds it back in, and runs the whole loop again to get cat. It might do that 10,000 times for one simple answer.
It's just brute force.
It's incredibly inefficient. And that brings us to the first breakthrough in our stack, diffusion language models.
Okay, now I know diffusion. That's the tech behind Midjourney and all the image generators. You start with static, with noise, and it slowly clears up into a picture.
Exactly. And Professor Stefano at Stanford, who's a pioneer in image diffusion,
Hmm.
he looked at that process and asked, why can't we do this for text?
But how does that work? You can't have blurry text. It's either a word or it isn't. You can't have, like, a fuzzy letter A.
You'd be surprised. You start with pure noise. In text terms, that's just a jumble of random characters, or maybe vector noise, a complete mess.
Mhm.
And then iteratively, the model denoises it. It refines the chaos step by step until a coherent sentence just emerges.
So instead of writing word by word by word,
It generates the entire block of text simultaneously. The whole paragraph just sort of manifests at once.
that sounds like a magic trick. Why is that actually better than the linear way? Is it just for coolness points?
2 massive practical reasons. First, speed, because it's all parallel processing. It's handling the whole sequence at once. Stefano's labs are seeing speeds 10 times faster than current transformers for the same quality.
10 times faster. That changes the game for things like real-time voice or video. You wouldn't have that lag.
Hugely. But the second reason is the one that gets me excited structurally. It's the editor function.
Okay, explain that.
Well, because the model sees the text as a holistic block, like an image, the prompt doesn't have to be at the beginning. In a current LLM, if you want to change the middle of a paragraph, the model really struggles because it can't see the future text it already wrote.
Right, it gets confused.
It gets confused because it only knows what came before.
It loses the flow because it's blind to the end of the sentence.
Exactly. But a diffusion model can drop right into the middle of a sentence, change 5 words, and simultaneously adjust the beginning and the end to make sure the grammar flows perfectly.
It's the difference between a typewriter and a Google Doc. You can just jump around.
It's a nonlinear editor. It's more like sculpting the text rather than printing it line by line. And because the network is constantly refining its own output, from noise to clarity, it has built-in error correction. It's not just guessing, it's iterating.
Okay, so that solves the writing problem, speed and editing. But there's another complaint I have, and I know listeners have it too. Memory.
The goldfish problem.
Yeah. I paste a long document, maybe a quarterly report, and by the time I ask a question about the conclusion, the AI seems to have forgotten the introduction. Or I have to pay a fortune for a model with a large context window.
This is the attention trap.
Yeah.
You know that famous paper that started this whole boom? Attention is all you need.
2017, yeah, the birth of the transformer.
Well, the mechanism they invented, self-attention, is brilliant, but it has this nasty mathematical side effect. To understand the context, the model compares every single word to every other word in the sequence.
So if I have a 10-word sentence, everyone gets introduced to everyone else.
Manageable. But what if you have a 100,000-word book?
That's a lot of handshakes.
It's quadratic complexity. That's the technical term. If you double the length of the text, the math doesn't get twice as hard. It gets 4 times as hard. Triple it, it's 9 times as hard. It just explodes exponentially. That's why your API bill goes through the roof for long documents.
So we hit a wall where it's just too expensive to remember everything.
Until now. And this brings us to the second breakthrough. Subquadratic, or what people are calling linear attention.
Linear certainly sounds cheaper than quadratic. How do they cheat the math?
Okay, imagine a cocktail party. The old way quadratic is forcing every guest to have a deep one-on-one conversation with every other guest just to get the vibe of the party.
Which takes forever and everyone gets tired.
The new way linear attention is like asking everyone to just announce their name and status to the room once. The model creates a single mathematical summary of the whole sequence.
A digest version.
Exactly. Now, historically, the trade-off was accuracy. You lost a lot of nuance with that summary. But companies like Manifest AI are developing these hybrid approaches. They call it power attention.
I was looking at their diagrams in the notes. They talk about staying on the diagonal line. What's that about?
It's a really smart compromise. They use the precise, heavy-duty attention for the immediate stuff, what we were talking about right now. But for the older context, what we said 10 minutes ago, they compress that into a linear summary.
So it keeps the sharp focus on the present, but keeps a running file on the past without clogging up the RAM.
Precisely. And the implication here is effectively infinite context. As long as you can efficiently compress the old stuff, you never really run out of room.
That feels huge. By 2026, could we just upload our entire hard drive to an AI and say, organize this?
That is the goal. A standard transformer simply cannot do that economically. This new architecture can.
Okay, moving on. We've got speed with diffusion and infinite memory with linear attention. But let's talk about the brain itself, because right now, even though these things seem smart, they are fundamentally limited by language.
What do you mean by that?
Well, ChatGPT thinks in English or Spanish. It predicts words. But human thought isn't always words. Sometimes it's images or feelings or a bit of logic that I can't quite articulate yet.
You've hit on a major constraint. Imagine if you had to speak every single thought you had out loud in perfect grammatical sentences at the exact moment you were having the thought.
I wouldn't get much done. And I'd probably say a lot of things I didn't mean.
We all would. Current models have to collapse their complex internal state into a single word choice at every single step. This really limits their reasoning power. The third breakthrough is what we call latent space thinking.
Latent space, it sounds like something from a sci-fi novel.
It's really just high-dimensional mathematics. The idea is to let the model think in its own internal language before it speaks to us. There was this fascinating finding from the DeepSeek R10 paper recently.
But I saw this. This is where the AI started making up its own language, right?
It was incredible. They stopped forcing the model to use human language for its internal reasoning, its chain of thought. They just rewarded it for getting the right answer. And what happened? It started inventing its own shorthand.
It created a code.
It mixed languages, it used strange symbols, it created these vector-like representations. It turns out English isn't the most efficient code for solving complex logic puzzles. When left alone, the AI optimized its own thinking process.
That's amazing, but I have to ask the obvious question here. Is that safe? If it's thinking in a language we can't read, how do we know it's not plotting something? Or more realistically, how do we know it's not just hallucinating and getting lucky?
And that's the big debate. But OpenAI is actually betting on this private thought strategy. And here is the counterintuitive safety point. When we force models to show their work in English, what we call chain of thought, they sometimes lie.
They lie.
They can be unfaithful. So they might output a chain of reasoning that looks good to you, the user, because the model predicts that's what you want to see.
Yeah.
but it doesn't actually reflect how the model got the answer. It's performing for you.
It's like a student showing the wrong math work but writing down the right answer because they peeked at the back of the book.
That's a perfect analogy. OpenAI argues that private internal reasoning might actually be safer because it aligns with the model's true beliefs and its actual process. We can't read it directly, but the outcome is more honest.
So we accept the black box in exchange for the truth.
We might have to.
All right, let's talk about learning, because right now, AI has amnesia. I can have a 3-hour brainstorming session with a bot, but if I come back a week later and start a new chat, it knows nothing about me unless I specifically remind it.
That's the static weight problem. The model is trained once, usually at a cost of millions of dollars, and then it's frozen. It doesn't learn from interactions.
It's read-only.
Breakthrough number 4 changes that. It's called nested learning, and Google is pushing hard on this.
Nested, like Russian dolls.
Sort of. It's a model within a model. The architecture separates the core model, the static brain, from a new memory layer.
But how does the memory layer know what to keep? I talk a lot of nonsense to my AI. It doesn't need to remember my grocery list from last Tuesday.
They use a surprise mechanism.
A surprise mechanism.
It's a filter.
Yeah.
The system analyzes the interaction. If the information is predictable or redundant, like you saying hello, it just discards it. But if something is surprising, new data, a correction you gave it, a really strong signal, it bubbles up.
So if I tell it, actually, I'm a vegetarian now, that's a surprise to the model based on previous data.
Exactly. And that signal rises to the top layer. This allows the model to have a real-time, updatable memory. It can know what's trending on Twitter this morning or remember your new coding workflow without risking the stability of the core model.
And without needing to retrain the whole thing from scratch, which is the really expensive part.
Right. It turns the AI from a static encyclopedia into a living, evolving partner.
Okay. We've covered speed, memory, thinking, and learning. But this last one, reading through the notes on this feels like the biggest shift of all. We're talking about replacing the concept of the transformer entirely.
This is the continuous thought machine, or
Oh.
CTM. And the irony here is just so rich because the paper proposing it was co-authored by Leon Jones.
Who is, famous note, one of the guys who wrote the original transformer paper.
The very same. He helped build the transformer, and now he's saying we need to move past it. His philosophy is that we stripped time and continuous dynamics out of AI to make it simple and scalable. We turn intelligence into a static pattern matching game.
He used an analogy in his presentation, a spiral. I really want to visualize this for the listener because it just clicked for me.
It's a great example. Imagine a data set shaped like a spiral, 2 colors swirling into the center.
Yeah.
If you ask the current transformer to separate the colors, it can do it. But if you zoom in, it does it by drawing these jagged straight lines, piecewise lines.
It's connecting the dots, but it doesn't see the curve.
It doesn't grok the concept of a spiral. It's just memorizing local patterns. If you asked it to extend the spiral outward, it would fail. It would just draw a straight line off the page.
And the continuous thought machine.
It represents the spiral as a spiral. It captures the geometry and the dynamics. It uses differential equations, math that describes change over time, rather than just static algebra.
And this isn't just theory. They tested this on mazes, right?
The maze benchmark. They put transformers and CTMs into a maze without a map, no God view. They had to figure it out step by step. Transformers just fell apart after about 20 steps. They couldn't hold the path in their head.
It got lost.
Completely. But the CTM, it was trained on 100-step mazes, and then, and this is the kicker, they dropped it into an 800-step maze.
An 800-step maze, that's massive compared to the training data.
And it solved it.
Wow.
That is a fundamental leap in generalization. The transformer memorized the 100-step solution. The CTM learned the procedure of pathfinding. It learned how to solve a maze.
That's the difference between memorizing a textbook and actually understanding the subject.
Exactly. And there's one more feature of the CTM that I just love. It has a native confidence variable.
Which means what?
Current LLMs are notorious for confident hallucinations. They will lie to your face with total conviction because they always have to output the next token. The CTM, on the other hand, tracks how sure it is. If the confidence drops, it can choose to take more time to think before answering.
It can pause and reflect.
It regulates its own compute based on how difficult the problem is. That is very, very human.
It sounds incredible. A model that understands concepts, generalizes to new situations, and knows when it's confused. So, the trillion-dollar question. Why aren't we using this right now? Why is ChatGPT still running on transformers?
This brings us to part 6, the barrier to entry. It's the inertia problem.
Is it just that companies are lazy? or risk-averse?
Not lazy. Invested. Think about the global AI infrastructure right now. We're talking about hundreds of billions of dollars of GPUs from NVIDIA, data centers the size of small cities.
All built for transformers.
We built the highways for one specific type of car. The transformer is highly parallelizable. It runs great on GPUs. The continuous thought machine right now is sequential. It's solving a differential equation over time.
So it's slow on current hardware.
It's hard to train efficiently. Leon Jones calls it the crushingly better rule. It's not enough for new architecture to be a little better, or even significantly better at reasoning. To justify ripping out the entire hardware and software stack of the global economy, the new tech has to be crushingly better.
Like transformers were crushingly better than the old recurrent neural networks back in 2017.
Yes. We're in that awkward phase where we have the blueprints for a Ferrari, but all our factories are only set up to build Fords.
But the history of tech tells us that better eventually wins out.
Always. The efficiency of the CTM, the reasoning of latent space, these advantages are just too big to ignore.
So let's bring this all together. If I'm looking at the next 18 months, I shouldn't expect just a smarter ChatGPT. I should expect a real structural shift.
We are moving from static, word-predicting typewriters to systems that are, well, they're more like sculptors.
Sculptors using diffusion to craft text.
They'll have infinite memory files using power attention.
They'll think in abstract math using latent space. They'll learn from us daily using nested learning. And eventually, they will understand the geometry of problems using continuous thought machines.
That's the roadmap.
And the timeline. The source said next 18 months. Is that realistic?
That's when we expect to see these shifts materialize in products. We're likely to see hybrid models first, standard transformers bolted onto these new memory or reasoning modules. You might see a reasoning mode that uses CTM or a creative mode that uses diffusion. The transition is underway.
It's exciting, but it also makes you realize how primitive our current cutting-edge tools really are. We think we're in the future, but we're still using the prototype.
We're still in the early innings, maybe just the warm-ups.
Before we wrap up, I want to leave the listener with a thought from the very end of our research stack. There's a prediction from Epoch AI that by 2030, AI will be solving open mathematical conjectures, problems humans haven't been able to crack for centuries.
It's a plausible timeline, for sure.
But if we look at that latent space breakthrough we just discussed, if the model is thinking in a language we can't read, to solve math we can't do, are we ready for that?
That is the ultimate question of alignment, isn't it?
Yeah.
We might be building an oracle that can give us the answers to the universe, but can't explain how it got there. We have to decide if we care more about the answer or the understanding.
A black box that knows more than we do. Something to chew on. That's it for this deep dive. Thanks for listening, and we'll catch you on the next one.